So we're now into the last part of the course. So this is the fourth major section in the course. And so the topic of this section of the course is something called generics. So we've already looked at the four parts of the object model. So we have abstraction, encapsulation, modularity, and hierarchy. So hierarchy is inheritance and interfaces. In many modern languages, people consider the fifth part of the object model to be generics. But you can have generics in any programming language. So most modern programming languages have some notion of generic type. Right? And so to explain what a generic type is, I'm going to review the our stack classes. Right? So we have two types of stacks so far. We have an int stack that can hold a stack of ints, and we have a string stack that can hold a stack of strings. If you actually look at the implementation of int stack, you can see that it's relatively straightforward. It's not a large class, right? So notice that one of our fields is an array that holds the ints in our stack. Right? The push method takes an int as one of its inputs, so push an int onto the stack, and pop, of course, returns an int, so pop the top int off of the stack. Now, if you want a stack of strings and you don't know about generics, you're kind of stuck at this point, right? So before the language introduced generics, one solution would be to make a stack of strings. So you would take your int stack class, you would copy it, or you would re-implement it to produce a stack of strings. So for example, you can make a string stack class, right, which looks like that, right? And notice that when you do this change, there's only 1, 2, 3, 4 locations where something actually changes. Everything else is the same, right? The name of the field is the same, the name of that field is the same, the name of the method is the same. The methods have different inputs and returns, but otherwise the changes are very superficial. Right? If you look at the implementation of the methods, you'll realize that the changes are very superficial. Right? So if you go and look at pop for int stack, oh, sorry. So this is pop for the int stack, but I've changed it so it now returns a string. Right? So there's your return type there. There's your element type there. So when you get an element out of the stack, you're getting a string. Right? And that's it. Again, the only changes that occur are with the types. All other code remains the same. So the only thing that changes are related to the type declarations. Right? All you do is take string and replace int in a few places. Right? And so, I mean, wouldn't it be nice if we could get the compiler to do this for us? Right? Compiler ought to be able to do this. You ought to be able to program a machine to be able to do this for you. All you're changing are some types. Right? And so that's exactly what generics are for in Java. Right? We're going to get the compiler to fiddle with the types for us to produce a stack that can hold any specified kind of element. Okay, so the generics are weird in Java because they weren't introduced until version 5 or 6 of the language. And so people were using Java for many years before the language designers actually got around to addressing this issue. You might think this is weird because it would be very useful to make a stack that can hold a specific type of element without having to write a new class every time. Right. Even when the language first came out, there was already a language that could do this sort of stuff, right? So C++ has something called templates, which are essentially generics. And people have been programming in C for decades, and they've been doing something similar in C. But this still happens today. So there are still modern programming languages that have to be updated, that are relatively modern programming languages that needed to be updated to put generics into the language. So before they put in a formal generics mechanism in Java, what people would do is they would make collections of big O object. Right? This works because you can store any reference in a big O object reference. Right. So for example, instead of making a class of that can hold just ints, sorry, a stack that can hold just ints, you could easily make a class that could hold a stack class that could hold one or more object references. Right. So for example, if you take the list stack that we have, a list-based stack that we had, and then if you put in an array list of big O object, right, you've now got a stack that can hold any type of reference type. You don't have to change anything. All you have to do is change what used to be integer or string to big O object, and now everything works. Right? When you push an element onto the stack, you push a reference to a big O object. When you pop an element off the stack, you get a reference to a big O object. So this works, but it's a little bit inconvenient. Right? So the problem is that your type of element is declared to be big O object. Right? So normally when you have a stack or a list or something like that, you know what element type is in it. When you get something out of the collection, you know what's coming out is, for example, a string. And you'd like to be able to use it right away as though it were a string. The problem here is that whenever you pop something, you get a big O object. Right? And so when you pop an element from the stack, before you use the object, often you have to cast it to something else. Right? So for example, here's my stack of objects, but I know it only holds strings, right? So when I use the stack, I'm careful to only put strings onto the stack. Right, so I've got a string stack, I push 3 strings onto the stack. Right? And I would now like to get a string off the top of the stack. Right, so I want to write string s equals stack.pop, but that doesn't work. Right, because pop returns a big O object. Right, and a big O object is not substitutable for a string. Right, the relationship is the other way around. Right, string is substitutable for big O object. So I can't write that. Right, if I try to write that, the compiler complains, says, "Hey, an object reference cannot be stored in a string variable." So what do you have to do when you pop the stack? You need a cast. So I have to cast a reference to string every time, and that's somewhat inconvenient. Right, after you do the cast, though, you can go ahead and use s as though it were a string. Right, so a little inconvenient, but there's actually a worse problem. Right, when you make a stack of object, you throw away type safety. Right? So for example, you can make a stack of object and now you can push anything onto the stack. Right? Because it holds, the stack holds object references. It doesn't hold references to some specific type. So if I make a stack that I know only holds strings, or I know should only hold strings, there's nothing stopping someone else who gets a reference to the stack from pushing something else onto the stack. Right. So for example, you have a stack that's supposed to only hold strings, and now somebody pushes a date onto the stack. The problem here is that the compiler can't help you here. Right? As far as the compiler is concerned, your stack is a collection of objects. So it'll let you push anything onto that stack. When you pop something off the stack, as far as the compiler is concerned, it's a big O object coming out. Right? There's no way for the compiler to tell you or to help you figure out what is the element type that's actually there. Right, so for example, there's my string stack again. Right, push three strings onto the stack. That's great. But somebody can push a 1 onto the stack, which is weird because that's an int. Right, that's not an object reference, but it works. The compiler happily accepts this. Right, it converts the 1 to a big I integer, pushes a big I integer reference onto the stack. Right, you can make another stack and push that stack onto the stack. Right? You can make a date, push the date onto the stack. They're all objects, so they're all substitutable for big O object. Right? All of this works. And because this works, right, this makes it impossible to write a method that is type safe. Right? So for example, it's impossible to write a method that takes in a stack of integers that always works, because someone can give you a stack and there might not be an integer on it. Right? So the compiler, again, can't help you here. Right? You can write this method. You can write a program that uses the method that seems to be correct as long as you always give it a stack of integers. Right? But as soon as you give it a stack that has something else, the method suddenly fails. Right? So compiles cleanly can fail at runtime. So for example, here's a method that sums the elements on that stack. It also clears the stack because the way this works is it just pops all the elements off the stack. Right. So here, there's a precondition on the method that that stack has only integers in it. Right. So when you pop the stack, you get a big O object coming out. right? So I need to cast elem to something that's to an integer so that I can actually add it to the sum, right? Notice the cast here has to be the big I integer. You can't cast it to int in this case, it won't work, right? So that's the other problem with generics in Java, is that the generic types are always reference types, right? So your stack of int isn't really a stack of int, it's a stack of big I integer. So when you pop that stack, you get an object out, you can cast the object to big I integer, but you can't cast any reference to primitive type. That doesn't work, right? So you're stuck with an integer, and now you can take that integer and sum it and add it to the sum, right? That code compiles cleanly. Compiler doesn't complain about it. There's no warnings. If you run it and pass it in a stack of int, everything's fine. You get the correct sum, assuming it doesn't overflow, right? Whoops, sorry. But as soon as someone passes in a stack that doesn't contain an int, that line fails right there, right? So for example, if that stack has a string on it, when it takes the object elem and tries to cast that string to an integer, it fails, right? And you get a class cast exception at this point, right? And code that once seemed to be correct is no longer correct, right? And there's no way to make this safe, right? I guess the best thing that you can try to do here is try to deal with the exception somehow, right? Check if the element type actually is an instance of integer. If it is, go ahead and do the cast, right? If it's not an instance of integer, I guess you have to do something else, right? Either ignore the value, throw an exception, or something. So that's less than ideal here as well, right? If you programmed in Python, this is exactly the data type you get in Python, right? So Python collections can hold references to any type, and there's no way to force it to hold references only to a single type, right? So Python collections aren't type safe either. And the same thing happens in C if they taught you how to make a collection that holds pointers to void, right? So you can make a generic collection in C where all of your elements are pointers to void, right? When you add elements to the collection, you create pointers to the elements instead of saving the elements themselves in the collection, right? The problem there is that you've got a collection that is pointers to void, right? So you actually don't know what the elements are in the collection anymore either. All right, so the solution to this problem in the Java language is you can create a class where one of your inputs to the class is the type as one or more types. Right. So we say that generics allow us to parameterize a class, an interface, or a method over types. Right. So for example, you can create a class where you have to specify what is the type that you want this class to use. So when you write new array list angled bracket string, you're saying you want a list of strings, right? That string is one of your parameters to your class, right? What this lets you do is instead of making a whole bunch of classes that are all stacks that are only superficially different from one another, you make one class, and that one class is able to deal with all sort. You make one class where you pass in the type, like this, right? And now the class ensures that when you make a stack of big I integer, you only have integers. You can only store and return integers. When you have a stack of string, you can only push and pop strings on and off the stack, onto and off the stack, right? And so on and so on and so forth. Right? And so these types of classes are type safe, right? So in Java, the language designers decided they wanted type safety over being able to put over flexibility, right? So instead of being able to put any element into your class, right, you can only put a specific type of element into your stack. Okay, so how does this work in Java? So you make a class that you want to be, where you want one or more of your types to be variables to your class. Right, those are called your type parameters. So you put the type parameters inside the angled brackets. Right. So when you create the class, you don't actually put in, normally you don't put in a specific type, right? So what you put in here is a placeholder for a type, right? So typically there's names like T1, T2, or T, or E, or something like that, right? And so the name here is just a placeholder for a type, Right? So T1 is some type that the user of the class is going to specify. T2 is a second type that the user is going to specify, and so on and so on and so on. Right? You can have as many of these types here as you want. So the angled brackets, they are the type parameter section, right? And the things inside are the type parameters, right? Or type variables. A limitation of the Java generic system is that these have to be reference type. So you can't make a stack of int, for example. There is a proposal though to fix that. I don't know if it's going to happen. Oh yes. Yeah, so that's what you have to do, right? So you have to, if you want a list of int, you have to make a list of integer instead, right? That's why the wrapper classes exist. Okay, so for these type parameters, when you create the class, most of the time you don't actually specify the type here. Is that true? Yes. So when you're creating a generic class, you actually never specify the actual type here. The user is going to specify the actual type. If you implement an interface or extend another class, you can put in the actual type here. But when you're creating a generic class, your type variables, they're just variable names, right? That's the best way to think about them. So typically, when you create these classes, your type name is just a single letter, or two at most. Right? So common letters that are used for the types, and is always in capital to indicate that it's a reference type, right? It would be E for element if you're making a collection of something. If you're making a map, right, you would use K and V, so for key and value. If your class deals strictly with numeric types, you might use big N for number, right? And then in general, if you don't have any particular reason to favor one of the other ones, you just use, big T for type, right? Or T1, T2, Tn, or STUV or something like that. Okay, so the simplest generic class that you can make, that's what we're going to implement right now. So in Java, you can only return a single value, right, from a method, and that's often inconvenient, right? So for example, if you're searching for the maximum value in a list, you might want to know what is the maximum value and where is it in the list, right? So you'd like to return two values in this case. In a language like Python, you can return multiple values from a function. In all of the C-like languages, you cannot, right? So you're kind of stuck here. You have to do something else. One solution in Java is you just make a simple generic class that can represent a pair of values, right? Where the pair of values can have any type. And so this particular class, so all we're going to do is use the class to hold two values. So I don't need a constructor. I don't need any methods, right? It's just really somewhat a mechanism to return two values. And so there is the simplest generic type that's actually useful that I can come up with. Right. So the class is called pair, right? It has two generic type variables, right? So T1 and T2. Right. Inside the class, you've got two public fields. Right. So anybody can access the fields just by using the name first and second. Right. The type of first is T1, the type of second is T2. Right. So now, if I would like to find the maximum value in a list of integer, and I'd also like to return the index of the maximum value, right? I can make a pair object where the first element is a type integer, the second element has type integer, right? And I can store the maximum value in first. Oh, sorry, I can store the maximum value in second, and I can store the index of the maximum value in first. So it's just the straightforward look for the max in a list, right? Every time you find a larger element in the list, you just store the result in first and second of result. If this was a list of string, right, I don't have to change anything here except for that integer there, right? So the maximum value is now a string, its index is an integer. So you would make a pair of integer string, right? And similarly here, you would make a pair of integer string and then return the result down. Right? Otherwise, the method works for whatever type you want here. you can later on, we can even change this method so that whatever type this is also the same type that this is. So there's a way to turn this method into a generic method where the user doesn't actually, where you don't actually have to say it's a list of integer. It's a list of anything. As long as you can do some sort of comparison here. Okay, so that's great. So this looks like it might be useful. I can make a stack class that is generic, so it can be a stack of any element type. So why don't we try to do this? Right. So if you start with the array stack, right, I'd like to turn it into a generic class. So I put in my angle brackets, right? I put in some placeholder for the type. I'm going to use E here because it's the stack is a collection of elements. Most people would probably use T, but anyway, right? It doesn't, the name doesn't actually matter. It's just a placeholder. Right. Now our array stack uses uses an array of objects. Right. So here I want to write big E, right? Array of element type E. So that's what I want to write. We're going to see in a second that's a problem. So for example, if I made a stack of string, hopefully the compiler changes that to string and away you go. Right. And if you make a stack of double, hopefully the compiler changes that to big D double and away you go. Okay. So you go to implement your class, right? Nothing else changes, right? Top index, we're still going to keep track of where the top index of the element is, the element of the top, the index of the top element, where that is in the stack. Everything else stays the same, right? And then you go to implement your constructor. So in our constructor, we want to make an array type B, right? A generic array. And so you write that, right? You just make an array, so new. Right, to make an array, it's always the element type, square bracket, the capacity of the array, right? And as soon as you write that line down in Eclipse or in your favorite Java editor, right, it will indicate this is illegal, right? It'll tell you generic array creation not allowed, right? And now you start to scratch your head. You say, well, generics kind of suck. This isn't going to work, right? So that line causes a compilation error. So it turns out in Java, you're not allowed to make an array of generic type. And there is a good reason for this, right? The reason you can't do it is related to the fact that they added generics into the language late, right? So after the language had already been used, they realized they wanted to add generics to the language, and they discovered that arrays, in fact, are incompatible with generic types. Right. So I'll get to the explanation of why you can't do this shortly. Let's fix the problem for now, right? And so the solution is, well, I can't make it looks like I can't make a generic array, but I can certainly make an array of type big O object, right? And that fixes the problem because you can store any reference type in an array of object. So off we go. Go back, change your E to big O object now. Right. Now the constructor works, right? So I can make an array of type big O object, right? So that works just fine. Compiler's happy with that, right? Now, why do I have to do this? It's because of the way that arrays work in Java, right? So arrays in Java are said to be covariant. So if sub is a subtype of super, right? Then in Java, the way that arrays work is an array of sub is also a subtype of an array of super, right? And so that means if you have an array of string, right, that array is substitutable for an array of object, right? Because string is a subclass of object, and so an array of string is also a subclass of an array of object. So that's what they mean by the term covariant, right? If something is substitutable for another type, then an array of something is substitutable for an array of another type, of the type. Okay, so now the problem with this is that this causes all sorts of weird things to happen. Right. So does the following compile, right? So I have an array of big O object, right? Over here, I've got an array of big I integer. Go back to the previous slide. Is integer a subtype of object? The answer is yes, right? So is an array of integer a subtype of an array of object? The answer is yes. So this works, right? You can write that down. Compiler will not complain at all. right? I've got an array of one integer referenced by a variable objs. So the answer is yes, this compiles. Okay, does this work or does it compile? Right? So what's the type on the right-hand side? Right? So the actual type is a string. What's the type on the left-hand side? Well, objs0 is an object because objs is an array of objects. Right? So on the left-hand side, you've got a big O object. Right? Is a string a big O object? The answer is yes. So this compiles just fine. Right? Notice the problem though, your array is actually an array of integer. Right? And a string is not an integer. Right? So does it run? The answer is no. As soon as you run the code, right, this line barfs. Right? You get an exception saying hello, the string is not a big I integer. So you can't actually store it in the array. Right? Compiler can't help you here because as far as the compiler is concerned, what you wrote is legal. Right? Because of the way the language works. The error now occurs at runtime, which you don't want to happen. Right? You would like errors to be caught at compile time as opposed to at runtime. Right? Okay, so now how do generics work? Right? So if you make a generic collection of some kind, they are not covariant. Right? So generics are invariant. Right? If I have two different types, T1 and T2, right? Then if you make a list of T1, right, there is no relationship to the type list of T2. Right? There's no inheritance, there's no association, there's no dependency, there's nothing like that. Right? They are completely separate types. Right? And so this relationship does not apply. Right? Which means that arrays and collections of stuff behave differently in inheritance. Right? So what is the advantage of making them invariant? Right? So can I make an array list of integer and store that in a list of objects reference? Right? The answer is no. Right? An array list of integer, right? There's no relationship between these two, right? So whether this is list of string or a list of anything else, right? There's no relationship between this and list of object, right? So that is not substitutable for a list of object, right? And the compiler stops this from happening, right? Which prevents this problem from happening later on, right? And so that's why the language designers prevented you from creating an array of generic type. Right, the arrays and generics don't play nicely together. Once you've gotten past the lack of generic arrays, so once you decided I'm going to use an array of object instead, push and pop now become straightforward to implement. Right, you still only need very minor changes. Right, so here's the complete version of push. Right, now notice that instead of pushing an int or a string, right, your element type becomes the generic type. So it becomes whatever the element type happens to be. Our placeholder is just E. Right? Now here, sorry, let's ignore this for a second. Where's here? Push. Okay, so in push, you're going to store whatever the element is in this array. Right? Now remember that array is an array of big O object. Right? So I can store any reference type in the array this.stack. Right? There's no problem there. If I have to resize the array, well, I just have to resize my stack, right? So use arrays copy of to make a new stack that's twice as big as the existing stack, right? It's still an array of objects. So there's nothing to do here either, right? There's exactly two changes right there and right there. And what about pop? Pop is slightly more complicated. So pop is going to return an element of type E back to the caller. Now remember, our stack is actually holding the elements as an array of big O object. So when you get something out of the stack, right? So in other words, when you access the array, the object that you get back is a big O object. Right? So before I return it to the caller, I need to cast it to type E. And so this is legal, right? So you can cast to a generic type inside of a generic class or a generic method, right? So I know from push right? I know that the only type coming into the stack, it's always of this type E, right? Where E is the generic type specified by the user. Right. So this cast here is always safe, right? I know that the elements in the array always have type E, so I can always cast back to type E. Right. So there's the change there, there's a change here, and that's it. Right. Oh, and there's a third change up here to the type that's returned by pop. Right. Everything else stays the same. So converting an existing class to a generic class is normally very simple, right? You have to hunt down all of your types that might change, and you just replace them with the generic type. Sometimes you have to cast stuff if you have an array of stuff, right? If you have an array of some type, you might have to make it an array of object instead of a generic array, right? But otherwise, everything's very straightforward. Right, so it's super the interface is even easier. Right, so remember we have a stack interface that was for a stack of string. Converting it to a stack of a generic stack is even easier than converting the class, right? You just add the generic type variable to the interface name and you change some strings to E. There's the original stack interface, right? It takes in a string, push takes in a string, pop returns a string, right? To turn it into a generic interface, add the generic type here, right? Change string to E here, change string to E there, and now you have a generic interface. Right. So converting regular interface to a generic interface, again, it's normally very easy. All right, we're almost done, right? So to complete our generic class, right, we can now say it implements a generic interface. So our array stack of type E now implements the interface stack of type E. Right, and that's it. And so there you've got a complete generic array-based stack implementation. That's it. So the advantage of doing this is that you've now got a stack that works for any element type that you want that the user wants to create. Right, you don't have to create multiple different classes for each element type, which is impossible anyway because you have no idea what element type some arbitrary user might want to have. Right? You don't have to go with a stack of big O object, right? Because that's not type safe. Right? Using the Java's generic mechanism, you now have type safe generic classes, which is nice. I guess what else? So Python doesn't have type safe generic types. It has generic types, but they're not type safe. Right. So if you were to if you have a list of stuff in Python, it's a list of object. Whatever Python's base object type is. I don't know what that is. But you can put anything you want into a Python list. A string in, then a number, then a double, and then a state, and then something else. Right. And it works that always works in Python. C++ has a mechanism called templates. It works similar to how Java works. So you specify a generic type, and then the compiler synthesizes a new type for every generic type that you use. All right, what time is it? Oh, it's only, okay, so I guess we should go on to the next lecture. So I'll have to download that one. The lecture slides are misnumbered, by the way. So if you download 26, it's actually 27 that comes. So somewhere I screwed up the numbering, and so that's why it jumps from 26 to 28. They're just misnumbered. There's not actually a missing lecture here. Oh, sorry, this is very slow. I should have downloaded this before class. All right, so let's look at another example of implementing a generic class. And so instead of a stack, we might as well try a queue. Hopefully this is just review for all of you. Right. So remember, you know what a queue is, right? From your previous data structure source? Yes. Okay. So remember what a queue is. It's basically modeling a queue or a line of people or something, a line of stuff, right? There's a front of the queue, there's a back of the queue. Right. So the first person in this case that's served is the person at the front. right? Every new person that shows up joins the queue at the back, right? So like a stack, queues only support two operations. There's NQ and DQ, right? So NQ, you add to the back of the queue. DQ, you remove from the front of the queue. Right? Some queue implementations call this push and pop. So they use the same notation that a stack uses. But classically, it's NQ and DQ. Right? Of course, you can have other operations on a queue. Right? You can have a size method that returns the number of elements in the queue. Right? Is empty, is the queue empty? Right? Peek is often available for stacks and queues. So peek lets you get the front element of a queue without removing it. It lets you look at the top element of a stack without removing it. Right? Some queue and stack implementations let you search the collection. Right? So there's contains. Right? In Java, you would probably put in toString. You'd probably put in equals. Right? So two queues are equal if they have the same collection of objects in the same order. So for NQ, the picture is useful because we're going to use the picture to help us implement the queue. So if you start out with an empty queue, oops, sorry, right? F and B, these are going to be references to the front and back element of the queue, right? So in an empty queue, I'm going to draw them as pointing at nothing, right? If you NQ one element into the queue, right, you've got one element, so F and B, front and back, they both point at the same element. Right? If you NQ another element into the queue, right, it's B that needs to change. So B now refers to the new back element. Right? So whenever you NQ, you're always going to adjust B. F never changes when you NQ. There it is. Right? When you DQ, right, the elements are going to come out from the front of the queue. Okay, so this picture is going to be misleading because we don't want to do it this way. So A comes out, and now in a physical queue, everybody shuffles forward one position. Right? If you're going to implement this using an array or a list, you don't want to do it this way, right? Because if to shuffle all of the other elements forward one position in the array or list is going to take O(n) time, right? Where n's the number of elements in the queue. So you don't want to do it this way. We want to do it some other way, right? But notice that the only thing that changes here is F, right? B never changes. B always points at the back element. So it's only F that's changing here. It's all right. There's a delay in the animation. More time, right? And so when you get down to one element, again, F and D both point at the same element, right? And finally, when you DQ the last element, F and B are again pointing at the same element, pointing at nothing in this case, right? So queues are first in, first out data structures, right? The first element that goes into the queue is the first element that comes out, right? They're also called last in, last out. Last element into the queue is the last element out of the queue. Right? In computer science and in computer engineering, these show up all over the place, right? Anywhere where there's a resource where only one thing can access the resource is probably managed with a queue or a priority queue, right? So web server, for example, has a queue of all of the requests that have come into the web server, right? Every time you click on a link, your request goes into a queue, right? If a million people click on the link at the same time, they all get put into a queue and then they get serviced one at a time, right? Your computer has many queues inside of it somewhere, right? Because there's all sorts of resources that your computer has to manage, and it can only serve one process at a time. Right? In networking, there's also queues that are used in networking. Many algorithms are implemented using queues. So breadth first search is typically implemented using a queue. And there's even a branch of mathematics that deals strictly with queuing. So queuing theory, I don't know if there's actually a course at Queen's that deals with this, but there is an entire branch of mathematics that studies queues. Right. All right, so we know about generics, we know about interfaces. We might as well start by creating a generic interface instead of creating a specific interface of some type and then changing it later on. Right? So everything works the same way. If I want a queue interface, I make an interface. Right? It's going to be called big Q queue, and it's going to be generic. So I can have a queue of some element type E. Right? We want a size method. We want is empty. is empty is the default method because I can just use size. Right. I want NQ and DQ, and I would like a front and back. So front lets you look at the front element without removing it. Back lets you look at the back element without removing it. All right. Okay, so if you're going to implement this using a list, then that's basically the exact same as implementing it with a stack, right? Except DQ removes the front element from the list instead of removing the back element. This is going to be problematic. Okay, the implementation though is dead simple, right? So I'm going to make a class called list queue. Internally, it uses a list of some kind to manage the queue. Right. Here I'm going to use array list, which turns out to be a bad choice. Anyway, I'm going to use array list here. Right. The size method is easy. I just check what is the size of this dot queue. Right. So what is the size of my list? NQ is easy. It's exactly the same as push for stack. Right. Simply add the element to the end of the list. Pop throws an exception if the queue is empty. Otherwise, it removes the front element from the list. Right. So the problem with removing the front element from an array-based list is that the way it works is all of the elements shuffle forward one position. Right. So you remove the first element, everything else has to move forward one position. So it's exactly like the picture showed you earlier. Right. When you remove from the front of an array-based list, that has complexity big O of n. Right. I have to shuffle all the remaining elements forward one position in the array. We would like to avoid this operation right there, right? Because I don't want one of the fundamental operations to be in big O(n) if I can make it faster. Right. The other methods are easy, right? To get the front element of the queue, you just get the first element of the list. Right. To get the back element of the queue, you just get the back element of the list. String's easy too. I can just call toString on the list and away you go. Equals also easy, right? Return this dot queue equals whatever, obj. Right. And so these are all pretty straightforward. Okay, so I want to avoid this big O of n here. So you can do it if you use a plain old array and you manage the DQ method yourself, right? So you have to deal with the fact that unlike a stack, NQ and DQ operate on opposite ends of the array. And so that complicates the implementation somewhat, right? It's not super complicated, but it's a little bit tricky. Oops, sorry. Right. So where the stack had two fields, the array and the location of the, sorry, it had two fields, the location and the element of the top index. Here I'm going to use 4, right? So here I'm going to have the array to hold the elements. I'm going to have another field called size, which holds the number of elements in the queue, right? I don't need this in the stack because I can just use top for that. It's the same thing, right? I'm going to have front, which is the index of the element currently at the front of the queue. And I'm going to have back, which is the element of the index of the element at the back of the queue. Right. So if you forget what these are, come back and look at this table here. The definitions are useful when you look at the implementation. All right, so I'm going to make a new empty queue. Right. So in an empty queue, there is no front or back element. So I need to decide what am I going to use for the values of front and back, or do I even care? Right. So I'm going to arbitrarily decide that for an empty, brand new empty queue, front will be 0 and back will be -1. Right. It turns out these values are not significant because the size of the queue will be 0. Okay, so when I NQ an element onto this queue, that's going to look a lot like pushing an element onto an array-based stack. Right. So array length. Am I calling it length? Like, sorry, typo. Array length. There we go. Okay, If the length of the array is equal to the size of the queue, then I know that I'm out of space in the array, right? So resize the array, reassign the array field to point at the new array, and then add the element to the end of the queue. Right? If there's space in the array, I'm going to move back one position to the right. Right? So back is going to shift over one position to the right, and I'm going to set the element at array back to the enqueued element. So back serves the same purpose as top in a stack. So after I enqueue one element, back was -1, it's now 1. Sorry, it's now 0. Right? Add the element into the array at index back, and increase the size by 1. Is that missing? Step 4, increase the size by 1. Right? Enqueue again. So back moves one position to the right. Right? Set the element at back, increase the size of the stack by 1, so it's now 2. Right? You do this again, again, and again. Whoops, sorry. There we go. So we've done it 5 times now. Right? And notice that back is to the right of front. So what about dequeuing the element? Right? So to dequeue the element, I want to remove the E. Right? So before I remove the E, I'm going to remember what it is, so I can hand it back to the caller. Right? So elem is going to be whatever's sitting at array up front. Sorry, what am I doing? I'm getting confused with the stack. I want to remove the A from the stack, from the queue. Right? I like to remove the that thing there. So I'm going to remember what is the element sitting at the current front index. Right? I'm now going to remove that element from the array in this case. So I'm going to null it out. Right? Now we didn't do this when we had a stack of int. Right? So in a stack of int, we didn't bother to zero out the value. If you have a generic queue or a generic stack, you want to null out the value here, right? Because remember, what's in the array is actually a reference to an object, right? If I don't remove that reference from the array, then whatever object is being pointed at can't be removed from memory, right? So if I null out this value though, right, that means the array no longer has a reference to the object. If the caller doesn't use the returned reference for anything, the virtual machine can now remove that object from memory because there's no more references to that object. So if you're implementing a generic structure like this using an array, you should probably null out the values. So that lets the virtual machine free whatever memory is associated with the object if it's no longer needed. Okay. I can now move front one position to the right and return the element. Okay. So after removing or dequeuing the first element, right, I'm going to null out that value. I'm going to remember what it is. I'm going to null it out. I'm going to move front one position to the right, return the value back to the caller, and decrease the size of the queue by 1. Right, so there's now 4 elements in the queue. And you can do it again and again, right? Notice that you can get into the situation where front and back both have the same value, right? If I remove that one again, right, front now appears one position to the right of back, right? Or back is one less than front, right? Which is the same situation that we had when we had a brand new empty queue, right? You might say that, hey, I don't actually need to keep track of the number of elements in the queue, right? So I don't need that field called size because I can probably do some arithmetic to figure out how many elements are in the queue, right? You're going to shortly realize that that's not the case, right? So looking at this situation, so if you have the situation where front is one position to the right of back, that doesn't necessarily mean the queue is empty. Something else could be happening here. So in other words, there's no reliable way just by looking at front and back to determine the number of elements in the queue.